Good morning. So here is the solution of the first assignment of casing design and tubulars. So we can see this is the question 1. So question 1 is asking us to derive the bending force equation if the casing is not in the continuous contact with the borehole. So here's the solution of the first question. So we can see there is a figure which shows the bending of the pipe in a deviated valve. So we can see that R is equals to radius, theta is the dogleg severity, and then we should also be noted that the length of Y1 is equals to Y2, which is equals to the outer diameter of the pipe divided by 2. So when we move on to the solution, you can see that the outer pipe is actually subjected to deformation. The outer part is being stretched, which means that it is in tension. So the strain can be calculated by dividing the change in length over the original length. So the change in length at the outer part of the pipe is equals to L plus delta L minus with L over the original length of the pipe, which is the L. So eventually we will get delta L over L is the strain. So delta L can also be expressed in other terms, in terms of the radius and also the log-leg severity. So it's given by the equation here. Delta L is equals to R plus Y2 multiplies by the dog-leg severity minus radius multiplies dog-leg severity is equals to Y2 and multiplies with the dog-leg severity. So after bending, we will get the Young's modulus, which is also known as the modulus of elasticity, is equals to the change in bending stress over strain. So this formula we have actually learned it earlier in the class before. So when we rearrange the equation, we will get the strain is equals to the change in stress over the Young's modulus. So this equation can also be put in terms of the change in length over with length, which is the strain that was derived earlier. So and then eventually we will get equation 1, which is the change in bending stress is equals to Young's modulus multiplies by Y2 over with radius. So the bending force is given by the stress multiplies by the area. So when we combine the first and the second equation, we will get the bending force is equals to the area multiplies by Young's modulus multiplies by Y2 over 12 theta over 100 and pi over 180. So as mentioned earlier in the figure, we assume that Y1 is equals to Y2, which is equals to the outer diameter of the pipe divided by 2. And over here, we also make the assumption that the nominal weight of the pipe is equals to 3.46 multiplies by the area. So when we substitute into the above equation, we will get FB is equals to 2 times 10 to the power of negative 6 multiplies by Wn E d naught and theta. So when we substitute the modulus of elasticity of steel, which is 3.0 times 10 to the power of 6 psi, we will get the bending force equation, which is 63 d naught Wn theta. So this is the final equation that we get. However, we should be noted that this equation can only be used when the pipe is in continuous contact with the valve bore. So in reality, it is not possible because of a few reasons. So first of all is because of the irregularities in the borehole. Besides, there is also the use of centralizer. So usually centralizer is being used to make sure that there is a certain amount of standoff. And last but not least, the radius of the pipe curvature is not constant. So we can see that there is no continuous contact of the pipe with the valve bore. So as mentioned earlier, it is not ideal to have continuous contact of the pipe with the valve bore. So here is a figure that is showing the bending of the casing that is supported at the casing collars. So we can see that the pipe is not really it is not continuously in contact with the valve bore, only the casing collars is touching the valve bore. Okay, so the radius of curvature of the pipe is given by 1 over R, which is equals to M over EI. The M is the bending moment and I is the moment of inertia, which can be computed by the equation of pi over 64 multiplies by outer diameter to the power of 4 and minus inner diameter of the pipe to the power of 4. So when we assume that the curvature of the bend section is small, we will differentiate it 2 times. 1 over r is equals to d2y over dx squared. So when we combine equation 4 and 5, we will get d2y over dx squared is equals to bending moment over E multiplies by moment of inertia. So by referring to the figure just now, the second figure, the bending moment mx is given by the equation number 7. So we can see that we actually cut off the wn x squared over 2 multiplies by sine theta and also the last term. So the reason that we are removing it is because they are negligible since the values is very small. So when we substitute the first equation that we derived earlier during the continuous contact with the valve bore into equation 6 and 7, we will get equation 8. And then after that, we assume that psi square is equals to Fa over Ei. So when we substitute the term psi into equation 8, we will get d2y over dx square minus with psi square y is equals to 2 times the bending stress over E d naught plus with Fwx over Ei. So when we integrate equation number 9, we will get equation number 10. So later on, we will set the boundary conditions. So there are two boundary conditions that are important. The first one, there is no pipe to wall contact. So we will get d2y over dx squared is equals to 0. And next one, the boundary condition is that the midpoint of the joint must be parallel to the borehole. So we will get dy over dx is equals to 1 over 2 multiplies by 1 over r. So when we apply the boundary conditions of these two into equation 10 earlier, we will get 1 over r is equals to this equation over here. So since r is equals to theta over L, we will get equation 11 after we substitute it into the above equation. So as we know, bending force is actually the stress multiplied by area. So when we substitute equation number 11 into equation number 12, we will then get Fb is equals to As E d naught theta over 2L multiplies by psi L over 2 and multiplies by 1 over tangent psi L divided by 2. Hence, after we simplify this equation and change it into the field units, we will get that the bending force is equal to the one that we wanted to derive earlier from the equation just now. So here is how we get to this bending force equation. So the next one is question 2. So question 2 is asking us to critically analyze the direct or indirect relationship of burst and collapse resistance with the following factors. So before we move on to burst and collapse resistance of the casing, we need to understand that these two properties are affected by the tensile load on casing. So the tensile load or the stress on the casing would reduce the minimum yield strength of the material, which then reduce the burst and collapse resistance. So we can see that the API burst pressure rating by the Barlow's equation is given by here. PBR is equals to 0.875. So 0.875 is assuming the minimum wall thickness by allowing 12.5% of tolerance of the nominal wall thickness. It's multiplied by 2 minimum yield strength thickness divided by the outer diameter of the casing. So from this equation, we can see that the burst resistance is directly proportional to the minimum yield strength of the casing pipe. It is also directly proportional to thickness of the casing and inversely proportional to the outer diameter of the casing. So from this equation, we can conclude that the burst resistance is directly influenced by the minimum yield strength. So as mentioned earlier, minimum yield strength is directly influencing the tensile load because the higher minimum yield strength means that more tensile will be needed to elongate the material itself. So next one is the API collapse resistance that is given by Lim's equation. So PCR is equals to 2 multiplies by minimum yield strength. So from 2 minimum yield strength multiplies by d naught over T minus with 1 over d naught over t to the power of 2. So similar to burst resistance, we can see that the collapse resistance is also directly proportional to the minimum yield strength of the casing pipe. Hence, we can conclude that the collapse resistance is directly influenced by the minimum yield strength. So next one, we will move on to the casing strength, which is as asked in the question. So the casing strength is expressed as the pipe body yield strength. So the pipe body yield strength is the minimum force that is required to cause a permanent deformation on the pipe. So the pipe body yield strength, which is given in the equation below, it is equals to minimum yield strength multiplied by this area. So from here we can see that the FA, which is the yield strength, is directly proportional to the minimum yield strength. So from here we can see that if the minimum yield strength is higher, a larger axial load or tensile load is needed in order to elongate the pipe. So if the minimum yield strength is high, the casing strength would also be increased. So hence we can see that the burst and collapse resistance are actually directly influenced by the casing strength. So the next one is the bending force. So when the case is being run into a deviated valve, the casing is subjected to bending force. So the equation of bending force is given here. So there are actually two equations as we learned in the question 1 earlier. We can either assume that it's in continuous contact or not in continuous contact with the bore hole. So due to the bending, the upper surface of the pipe will stretch and it is in tension, whereas the lower surface of the pipes will be shortened and is in compression. So this increase in the tensile load due to the bending force will actually decrease the minimum yield strength. And then after that, it will also decrease the burst rating and also collapse rating. So from here, we can see that PBR, they are actually directly influenced by the bending force, because once the bending force is increased, it will decrease the minimum yield strength, which then decrease the collapse and burst rating. So the next one is the suspended weight. So suspended weight is the weight of the pipe that is suspended below the casing hanger or the joint of the interest. So we can see that the suspended weight is actually reduced due to buoyancy force when it is immersed in the drilling fluid. So the equation is given by FA is equals to the weight of the pipe in air minus with the buoyancy force. So the suspended weight of the pipe itself will actually exert an axial force on the pipe. So when it exerts the axial force on the pipe, it will then decrease the minimum yield strength. So consequently, this will also decrease the burst and collapse rating. So from here, we can conclude that PBR and PCR, they are actually indirectly influenced by the suspended weight. So the next one is the shock load. So shock load, it will only act on a certain part of the pipe for a very short period of time. So when we are running the pipe and then it suddenly stops to set the slips, we will actually generate a compressive stress wave. So this stress wave will be reflected to the shoe and then reflected back to the top at the slip, and then the reflection eventually, this will actually result in a stress that is equals to twice the tensile stress at the slips. So the total shock load is given by the equation below. So what we can conclude is that the shock load will actually exert a tensile stress on the pipe, which will then decrease the minimum yield strength. Then after that, as we have learned earlier about the relationship, this will then decrease the burst and collapse rating. So hence, we can conclude that the burst and collapse rating are indirectly influenced by the shock load. So lastly, we will have the drag force. So when the casing strings are usually being rotated or reciprocated during the landing on cementing operations, so this will then result in the axial load due to the mechanical friction between the pipe and the bore hole. So the drag force is given by the equation below. It is the friction factor multiplied by the absolute value of the normal force. So what we can learn is that the drag force will actually exert the axial load on the pipe, which will then decrease the minimum yield strength. So consequently, this will also decrease the burst and collapse rating of the pipe. Hence, we can conclude that the PBR and PCR are indirectly influenced by the drag force. So just to conclude it again, the burst and collapse resistances of the casing are affected by the tensile load on casing. The tensile load or stress will reduce the minimum yield strength of the material. Hence, the burst and collapse are directly related to casing strength, as the casing strength will determine the minimum yield strength. Meanwhile, for the loading conditions, shock load, drag force, suspended weight, and bending load, the burst collapse are indirectly related to them, as the loadings will exert axial force on the pipe, which will then decrease the casing strength. So that is the end of the solution of the assignment. So here is the reference that is being used throughout this assignment. Thank you.